As you can see from the title of this video, this tutorial is about drawing Lewis structures for specifically ionic compounds. If we're going to take a look at this, we have to get a quick refresher on how is it that we can tell if a bond is ionic or covalent. If you remember, right, there are three types of bond: ionic, covalent, and metallic. In terms of drawing Lewis structures, you are only going to have to focus in on two: ionic and covalent. Seeing as this video is about exclusively ionic Lewis structures, I will simply focus on how we identify ionic bonds. By definition, an ionic bond is one where electrons get transferred. They totally leave one atom's electron cloud and they enter a different atom's electron cloud. How we know if something is going to be ionic or covalent has to do with a difference in electronegativity. Right? The more attractive one atom is than the other, the greater the chance there is that an electron will jump from one cloud to the other instead of getting shared like it would be in a covalent. The rule for remembering ionic bond types is that it is a metal plus a non-metal. If I bring in a picture of the periodic table, if you remember from when we learned about the table, it's divided into metals and non-metals. The red staircase that goes down the right side of the periodic table is the demarcation line between where are the metals and where are the non-metals. If you remember, metals lie to the left, non-metals lie to the right. So if I take something from the left with something from the right, I will get an ionic bond. I would have to draw an ionic Lewis structure. Remember, the only exception to that rule is hydrogen. Even though hydrogen technically lies to the left of the staircase, hydrogen with a non-metal most often will form a covalent bond. Occasionally you will see hydrogen with a metal when it refers to as a hydride, and then in that case it tends to be ionic. But we will really kind of save hydrogen non-metal for covalent structures. So, once I identify that a bond is ionic, I want to be able to draw a picture of what the bond looks like. Right? The transfer of electrons and how that occurs. So if we looked at a few examples, I could zero in on something like NaCl, sodium chloride. First thing I would do is identify it as ionic or covalent. Na is to the left of the staircase, Cl is to the right, therefore it's ionic. We must have an ionic bond. The key for ionic bonds, when we draw their Lewis structures, is that they are depicted by before and after pictures. If an ionic bond is a transfer of electrons, we want to see what does it look like before the electron gets transferred, and then again, what does it look like after the electron is transferred. So, if we are going to do this for sodium chloride, the first thing that I do is I draw each element individually with its electron dot structure or Lewis dot structure. Remember how we did this. If we find the element Na, to get the number of dots that they possess, I need to depict its valence electrons. Well, the nice thing about the periodic table is it orders things by columns of valence electrons. If you remember, group 1, I'll get 1 valence electron. 2, I'll get 2. The middle section and the bottom section all have 2 valence electrons as well, because these electrons go into orbitals that aren't the outermost shell. And then from 13 to 18, it matches the latter half. 13 gets 3, 14 gets 4, 15 gets 5, 16 gets 6, 17 gets 7, and 18 gets 8. and that's why the noble gases don't react. They have fulfilled the octet rule. So, if I am going to draw myself Lewis dot structures for each of these, right? NaCl has sodium and it has chlorine. Na is in group 1 on the periodic table, so it gets 1 dot. Chlorine is in group 17 on the table, therefore it gets 7 dots. And even though they're dot structures, I'm going to go ahead and make them a different symbol so we can tell the difference between chlorine's electrons and sodium's. I'll make chlorine's X's. 1, 2, 3, 4, 5, 6, 7. So if you take a look at what's going on here, what you'll see is that we have a case where sodium has 1 valence electron. 1 valence electron is very far from the octet of 8, so it is not very likely it's going to gain electrons. By losing an electron, what it can do, though, is it can reveal a complete subshell. Right? For instance, if I drew a picture of sodium which has 11, there's my nucleus. First energy level gets 2, 1s2. Second level gets 8, 2s2, 2p6, and then the third level just gets 1, 3s1. So there is my 1 valence. Right? The catch is this. If I lose this valence electron, there is nothing left in this outermost shell. And if I were to lose that outermost shell, look at what happens. The new outermost shell has 1, 2, 3, 4, 5, 6, 7, 8 valence electrons. So by losing the 1 dot on sodium, you actually fulfill the octet rule, which is what they all want to do. So sodium wants to lose 1. Chlorine is at 7. It's very close to 8. It wants to gain 1. So that is exactly what happens. The 1 electron of sodium gets transferred over to chlorine. That is what we refer to as the before picture. The after picture is I draw what is there after the electron leaves. I still have a sodium atom, but now it doesn't have 1 valence electron. It gave it away. It has none. If you remember, whenever you lose an electron, electrons are negative. If I give up a negative, I become positive. So sodium gave up 1 electron, so it will be Na plus 1. Chlorine, on the other hand, has the 7 X's that it initially did, plus now the dot from sodium. So it has 8 valence electrons. Chlorine gained an electron. Electrons are negative. If I accept a negative, I become negatively charged. I accepted 1 negative, so chlorine gets a -1 charge. So this is what we refer to as the after picture. What I want you to see here is that we have created a positive and a negative. And this is leading to opposite charge attraction. And that opposite charge attraction is what we define as an ionic bond. That positive being attracted to the negative creates an electrostatic force between them, and that is our ionic bond between sodium and chlorine. Ionic bonds are very strong. They are the strongest of the types of bonds that we will look at. They're the most difficult to break. They take the most energy. So let's try a couple more. Let's look at something like MgF2. First thing you need to do is decide, is it ionic or covalent? Taking a look, Mg is here to the left of the staircase. F is to the right of the staircase. That means it's a metal plus a non-metal. This will be ionic. If it's ionic, I need a before and after picture. So my before picture, I see that I have 1 Mg and that I have 2 Fs. Then we have to get our number of dots. Mg is in group 2, which means it gets 2 valence electrons. Fluorine is in group 17, which means it gets 7 valence electrons. And again, I'm going to make fluorines different than magnesium. And you can have fun with it here. You can make them hearts or footballs or X's or whatever. All right, so if we take a look at what's going to happen, it's pretty obvious that magnesium wants to lose electrons and fluorine wants to gain them. The general rule for figuring out who wants to lose and wants to gain, if you have less than 4, you tend to want to lose them to get to 0. If you have more than 4, you want to gain them to get to 8. And that's the 2 ways we fill the octet rule, by getting to 0 or getting to 8. So magnesium wants to lose 2, fluorine wants to gain 1. So what happens is, this fluorine wants an electron, so magnesium says, I will give you one, because it helps me fill my octet. This electron can't go to fluorine because it's already full. So this electron will go to the other fluorine. If I then go and draw my after picture, I'll still have 1 magnesium that now has no dots, and I'll have 2 fluorines, each of which has 7 dots now. I'm sorry, 8 dots. 7 X's and 1 dot. Last but not least, you need to take care of charge. Right? Magnesium lost 2 electrons. It gave up 2 negatives, which makes it more positive. So if you give up 2 electrons, you get a +2 charge. Fluorine, in each case, gained 1 electron. Do not say fluorine gained 2, because 2 fluorines gained 2, which means each one gained 1. Therefore, fluorine is -1. A good check to make sure you're doing these correctly is most often, the thing I start with on the left side is neutrally balanced electrically. Right? And on the right side, that has to be true. I can't create or lose charge. Right? I have to have the same charge on the left as I do on the right. So if the left is a 0, if I add up the charges on the right, they should add up to 0 as well. +2 -1 -1, sure enough, is my 0 charge. Sometimes it won't be as simple as them giving you the formula. They'll just tell you that 2 elements combine. Let's take a look at one that works like that. For instance, what if it said a bond is formed between potassium and sulfur? If a bond is formed between potassium and sulfur, I need to figure out not only what does the picture look like, but what will be the resulting formula from that bond. The trick to doing these is you start with 1 of each and then try to make everybody happy. For instance, if I have potassium and sulfur forming a bond, I will start with 1 potassium and 1 sulfur. Then I'll draw my dots, taking a look. Potassium, remember, is element K. It's over here in group 1. Group 1, I'll get 1 valence electron. Sulfur is right here. It's in group 16. Therefore, it gets 6 electrons. So, if we're going to try to make people happy, what happens is sulfur wants to gain, and potassium wants to lose. Potassium, is below 4, therefore it's going to lose to get to 0. Sulfur is above 4, it will gain to get to 8. So potassium will transfer an electron to sulfur. Potassium will be happy because it has 0, but sulfur will not be happy because now it has 7 valence, which is actually almost even worse than having 6 because it's so close to the octet rule, it really wants to get that 8th electron. Anytime you're just given the elements in name, there is no limit to how many of each you're allowed to have. So if I need another electron, I will bring in my source of electron givers, which is potassium. It gets 1 dot. And see if I can make sulfur happy by giving it this one. Now, if you take a look, I have 2 potassiums that both gave up their 1 dot, so they're happy. I have 1 sulfur that needed 2. It got 2, so now it is happy. So now we can draw our after picture. I still have 2 potassiums. They have no dots because they each gave up an electron. They are each a +1 charge. I have 1 sulfur. It now has 8 valence electrons. 6 that were X's, 2 that were dots that came from each of the potassiums, and it gained 2 electrons, therefore it is a -2 charge. So that's how you tackle one where you aren't given the formula, but they just give you the names of each of the elements. Let's try one like that again. For instance, say we're working with calcium and bromine. Again, I'm given the names, so I'll start with one of each. 1 calcium, 1 bromine. Calcium is in group 2, so it gets 2 dots. Bromine is in group 7, so it gets 7 dots. Given the scenario that we've drawn, calcium obviously wants to lose electrons, bromine wants to gain them. So calcium will give an electron to bromine, taking that bromine to 8, so it's happy, but calcium still has 1 left behind. So we need somewhere to put that other dot, and again, because I wasn't given the formula, I can bring in elements as I need them, and I'll bring in another bromine with 7 dots, and that second electron can get transferred down to bromine. Drawing my after picture, I will have 1 calcium with no dots, and because it gave up 2 electrons, Ca gets a +2 charge. And I have 2 separate bromines that now have 8 dots, 7 X's and a dot. And because each bromine gained 1 electron, they are both a -1 charge. Notice your charge adds up to 0. +2 -1 -1 is 0. And if I wanted to write a formula for the bond created between these, I have 1 Ca, I have 2 Brs, it would be CaBr2. Let's try one last one like that. Say we're working with aluminum and oxygen. Again, I wasn't given a formula, so I start with one of each of these. Aluminum is Al, oxygen is O. Right? Aluminum is in group 13, so it has 3 valence electrons. Oxygen is in group 16, so it has 6. So now we try to get everybody to 0 or 8. So aluminum has 3, it wants to get to 0, so it wants to lose. Oxygen has 6, so it wants to gain. So what happens is this one can get transferred here. Now oxygen has 7. This one can go here. Oxygen has 8. It's happy, but aluminum still has 1 left. It's not happy. So we have to bring in another oxygen. Oxygen still has 6 to start. Now we can get rid of that last electron from aluminum. It can go here. But now we have an oxygen down here that has 2, 4, 6, 7. It's 1 short. It needs more electrons. So we have to bring in another aluminum, which has 3 electrons. Well, oxygen needs 1, so aluminum can give it the 1. Right? But this aluminum still has 2 valence electrons, so we have to bring in another oxygen that starts with 6. And aluminum wants to get rid of 2 electrons, so 1 can go here, 1 can go here, and now you take a look. Everybody is happy. This aluminum gave 3 away, this gave 3 away, so they're both at 0. Each O needed to gain 2, and they all did. So now I can draw the after picture. For the after picture, I'll show you shorthand, but try to avoid this because most often as you're learning, people make mistakes. Right? People may ask, do I have to draw both bromines in this case? Right? Or can I do something to make less than that? Here's the reason why I don't like to do the shorthand. If we drew this, right, and I don't do shorthand, aluminum, I have 2 of them. Neither one has any electrons. They both gave up 3, so they would both be a plus 3. Then I have 3 oxygens, all with 8 valence electrons now. And each oxygen gained 2 electrons, so they're all a minus 2. Right, so plus 3, and minus 2, minus 2, minus 2, positive 6, negative 6, we're at 0, so that's good. Right? And the formula for this would be Al2O3. The reason I try not to abbreviate this when we do it is that there's a tendency for people to misrepresent what's happened. For instance, if I'm going to do this correctly, I have 2 ALs. At the end, I have 3 O's. The ALs have no dots. The O's all have 8. And where people make a mistake on is the charge. When they try to figure out the charge on aluminum, they'll say, oh, aluminum gave up 6, and they'll want to put a plus 6 here. Right? But that's not true. Aluminum only gave up 3. So it's 2 Al plus 3. And again, O is not a minus 6. Right? Each O is a minus 2, so it's a negative 2 here. Right? Sometimes people will try to go abbreviate this Al plus 6, O negative 6, which is untrue. This means there was 1 Al that gave up 6 and 1 O that gained 6. All right? And that doesn't make sense. All right? So if you're going to abbreviate and you want to try it that way, right, you have to put the number in front of the symbol, all right, that you should draw in the after. But to be honest, I think this way is just as easy. So that is how we tackle ionic Lewis structures. I hope this clears up any issues that you may have, but if it doesn't, please feel free to stop in for some help.